Good afternoon and welcome. Thanks for taking the time to come to this talk where we're going to talk about Storage Spaces Direct. The title of the presentation does not include that, but I think you all got it. So my name is Klaus Jorgensen. I'm a principal program manager at Microsoft. I've spent the last many years working on Storage Spaces Direct. And before that, I worked on the scale-out file server and SMB transparent failover capabilities that was introduced in Windows Server 2012. With me, I got Michael. And Michael is in our storage and file systems team. And he'll be talking a bunch of the cool stuff we've been doing with RDFS. And we also got Hector here. He's going to talk about System Center VMM management of Storage Spaces Direct. Let's get started. So I do have one slide of where we're currently at, but other than that, I won't talk too much about the existing situation. So in the Windows Server 2012 was really the first time we endeavored into software-defined storage. Previous to that, you would typically use SAN storage, whether fiber channel attached or iSCSI behind Windows servers. So we pushed into being able to use cost-effective standard volume hardware. Some of the key elements that was necessary in order to build a private cloud, like with hypervisors that could consume our storage, was that our storage could be continuously available. We would have scale out and reliability. Those are sort of the base platform that we laid in the Windows Server 2012 release. And we're also our management story. Now, in that release, our focus on software-defined storage was using effectively what we could call a shared JBOD storage, where you would have one or more JBODs. The JBODs would need to be physically connected to every single storage node in the cluster because every one of them needed direct access. So that bottom layer in the diagram on the right is effectively what we're going to be talking about today and how we're moving that forward. So introducing Storage Spaces Direct. So what is it? So Storage Spaces Direct is private cloud storage. So meaning storage that I can use to store my Hyper-V VM files on. Right? So in the difference from the prior release, we can now use servers with local disk, meaning disks that are sitting inside the server chassis or connected only to a single server. We maintain the high availability properties that we have today, but it does give us an element of scalability that is much wider because we don't need the physical connectivity. Well, I'll come back to that in a few minutes. It does enable some new scenarios to be unlocked that we'll be talking about. But finally, it's important for me to stress that Storage Spaces Direct is not a replacement of storage spaces as it is in Windows Server 2012 R2. It's an evolution of storage spaces that we introduced to now be able to consume a new set of hardware devices, meaning hardware devices that are sitting internal to the servers, which means we can use devices like low-cost flash storage using SATA SSDs, or improve the better flash performance using NVMe SSDs. Prior, we would always need SAS SSDs for flash. Using Storage Spaces Direct actually gives us a simpler deployment model because the network fabric we're using instead of a SAS fabric, the SAS fabric can be rather unwieldy when you have n number of nodes that needs to be connected to m number of JBODs, and everybody needs to be physically connected to every JBOD. So you can imagine how that can easily become more complex as you scale the number of nodes and you scale the number of JBODs. With Storage Spaces Direct, we simply attach each server to a high-speed networking infrastructure, and then we do all the data transfer over that networking infrastructure. It also brings with it the ability to use for simple hardware requirements. So we don't need disk devices that support persistent reservations. We don't need MPIO devices, etc. Seamless expansion is as it sees, is you can simply take, like if I have a diagram of a 4-node system here, you can simply add a 5th node to the system and include that in the storage cluster and then rebalance your data. And because of this architecture, it allows us to increase scalability because we don't need this physical connectivity anymore. So now we can scale to many more nodes, and we can also scale to many more disks. Now, before we go into the technical details on it, I also want to make sure that you're aware that there is a deployment choice. So we don't tell you to always deploy with the hypervisors and storage together, or always deploy with the hypervisor and storage separate. The Storage Spaces Direct, you can actually do both. So you can deploy it in what the industry has been dubbed hyperconverged, where the compute and storage resources are together on the same set of machines. That type of deployment means that you have the compute and storage resources are scaled and managed together, right? So as I move more machines into the system, I put an equal amount of CPU, memory, and storage into the system. This is relatively simple to deploy. So where we think this will head most is to like small to medium-sized deployments, where the ease of deployment is more important than the flexibility scaling independently. The other model you can deploy is what we've dubbed private cloud storage. That's where Storage Spaces Direct is used as storage for hypervisors as well, but the hypervisor, Hyper-V, is remote from the storage system. So the hypervisor is connecting over the SMB network to get to the storage system. So that allows you to scale the compute and storage resources independently. Right? So there's no interlock between the two. So if you need a bunch more CPU or memory, you just add more hypervisor machines. Keep storage the same. If you need a much more storage capacity, but you don't really need more compute capacity, you just scale more storage. So that we typically see already today with service providers and a lot that actually deploy a lot of machines. And we allow you to basically deploy whatever is the right choice for you. So one quick note, in the Windows Server 2016 Technical Preview 2, you can go ahead and try out the scenario on the right, and we'll do more testing on the hyperconverged scenario, so that we will recommend you try out in a future technical preview. Now, the other conversation is, okay, so you supported shared SAS in the past and support now, and you will support direct attached storage in the future. So when do I choose what? And both architectures will be supported in Windows Server 2016. So whatever investment you make today in hardware, you can run that hardware configuration when Windows Server 2016 you upgrade to that. You don't have to worry about us making a switch on you. We also allow you, of course, with Windows Server 2016 to run Storage Spaces Direct. So what's the key differences? So Storage Spaces with shared SAS actually do allow you to scale down to 2-node configurations, where you simply have 2 storage nodes and a single enclosure behind it with a cable from each node to that enclosure. That's a very small deployment. Whereas over on the Storage Spaces Direct, the minimum deployment is 4 nodes. The Storage Spaces with shared SAS also allows you to do dual parity with less hardware, because you could do dual parity across just the disks. Whereas when you run dual parity in a Storage Spaces Direct deployment, its default domain is the nodes, so therefore you would need 4 or more nodes for that. Now, on Storage Spaces Direct side, it unlocks the use of SATA and NVMe devices, which is super important for us, because those types of devices either drives down cost of flash or improves performance in flash. NVMe devices, for those of you that it may be new to, NVMe devices is effectively flash storage sitting on a PCI bus with a standardized NVMe interface to access it. And as you would probably guess, the PCI bus is a very efficient data transport. So you can do a lot of IOPS and throughput with NVMe devices that you normally not could do on a SATA interface. And the other difference is that with Storage Spaces Direct, you have very simple scalability. We don't have the complex SAS cabling. We can just add nodes and roll out as we need it. There we go. So let's spend just a minute, just open the hood real quick. This is not an architecture diagram, but it's a slightly conceptual architecture diagram. So we start with servers, physical servers, n number of physical servers with local disk. That's the whole premise of this thing, right? SATA, NVMe, SAS. I think you got that now. Then on top of that, what we have built is what we call the software storage bus. The software storage bus is a software implementation of a storage bus that effectively is us replacing the SAS shared infrastructure using software over an Ethernet fabric. That software bus spans the entire cluster, and we leverage our investments in SMB3 and SMB Direct to make that transport very fast and fault tolerant. So with SMB Direct, we can enable and utilize RDMA-enabled network infrastructures, which means that the latency we can drive down to as small as possible. Now, and I used to joke, I don't know if you know what the acronym of SMB is, but the acronym is Server Message Block, and it's always been used for file, but now it's actually being used for block. On top of that, since we now have built this software bus that spans the entire cluster, that makes it the ability to basically create a storage pool, just like in storage spaces today, you create a storage pool that it spans all the devices across all these machines. And then once you've done the storage pool, you create your resilient virtual disks where you define your resiliency characteristics. Should it be 2 copy? Should it be 3 copies? Should it be dual parity? All the existing resiliency schemes are still supported just in this configuration. Actually, at this point, the whole thing is abstracted to the point that a storage virtual disk doesn't know that it effectively runs on top of servers with local disks as opposed to shared SAS disks. Once we got all these virtual disks, then we put file systems on top. And the key thing here is that with this release, we're moving towards REFS being the primary file system for private cloud storage. And that's important. And Michael will cover that with 2 or 3 slides later on and a few demos. And we bind it all together in a cluster-wide file system with the CSVFS. And then further on the top that's actually where we first see the difference between the 2 deployment scenarios. Right? So you can have one where we run the scalar file server at the top for the private cloud storage scenario I had just before, or locally run the machines locally on the CSV file system. So what's the cool thing about this, at least I think it's cool, is that you can see that 80 to 90% is the same, regardless of whether you run with the hypervisor remote or the hypervisor local. And then, of course, we have System Center to manage all the layers in the architecture, from deployment, provisioning, etc. Now let's go in and talk a little bit about availability and scalability. But before I go there, I need to spend a little bit of time to talk about how Storage Spaces does data placement, because it's fundamental to understand the other pieces. So the virtual disk, and for those of you who are operating SANs, you can equate that to a LUN in your thinking. So a virtual disk consists of what is known as extents. Right? One extent is 1 gigabyte in size. So a 100 gigabyte virtual disk consists of 100 gigabyte extents. So if you look at the very simple disk on the right, we have a virtual disk with 3 extents. Then, when you take a 5-node cluster like this, the extents are distributed across the disks and the servers. So in this case, you can see extent A landed on server A, extent B on server B, etc. So that's how you scale out. Now, if you then have a 2-copy mirror on your virtual disk, then the second copy of the extent will be placed on a different server. So like A, you can see A prime is then on B. The purpose of that is, of course, to provide resiliency from a server either failing or being restarted or whatever is the reason that is temporarily or permanently out of commission. And similarly, if you have a third copy, then it goes on yet another machine. All right. So, scalability. Scaling to large pools. So one of the key things we wanted to do was, if you have looked at our documentation, the storage spaces in the current implementation would support around 80 disks in a pool. We want to push that number much higher. So we did a bunch of work in terms of scaling the size of the pool. And with the technical preview 2, you can run the pool up to 240 disks. And we really don't have any plans on stopping there. But I cannot give you the number for when we finally release, but it's going to be either that or higher than that. We use, I mentioned before, we have a fast interconnect. We utilize SMB3 and SMB Direct for all the, what you could call the east-west traffic in the storage system, as well as SMB3 for the interconnect to the hypervisors if it's remote from the system. That gives us very low latency, and it gives us very low CPU consumption because we can offload the data transport to the RDMA-enabled NICs. That means we don't have to spend CPU cycles doing TCP/IP processing. And that means we can give those CPU cycles to where they're really needed, the VMs that are actually doing the work that brings in the money for your company, right? Let's see. Am I pointing in the wrong direction? Oh, here we go. Simple expansion. You simply add node, expand the pool, and then you can rebalance. So what does that look like? So remember the extents that I was talking about? So here's a system that is 4 nodes, and we got extents spread around the system with the copies on other nodes. Now, if we simply add a 5th node, and you rebalance for capacity, in the background, we will move data extents from the most filled nodes to the most empty nodes. It's a background activity, very little impact on user I/O because that user I/O always takes priority, happens in the background, completely transparent, nothing needs to be taken down. So that's how we can do rebalancing. What that really gives you is that you can expand your system not only for additional capacity, but if you're running out of horsepower in your disk or in your flash devices, you could add a 5th node, and then you simply have more devices, but you don't have to reformat your data or create new virtual disks to take advantage of it, etc. It also works the other way. You can remove a system, and it'll fold data back into the remaining systems. So the scale for the Technical Preview 2, and I underscore it's for the Technical Preview 2, which is the one you can download now, is a minimum of 4 servers, a maximum of 12, and a maximum of 240 disk devices in a single pool. But I think that should be pretty good to get you started in testing and playing around with this stuff. Now let's spend a moment talking about availability. Because if your data is not available, it's not interesting, right? So we are fault tolerant to disk enclosure and server failures, right? We are resilient to 2 failures and partitioning. And all of these failure scenarios is with uninterrupted data access from the hypervisor. In this case, I show the hypervisor external. So the first scenario is that we have fault domains. So we treat the server as the default fault domain, right? So in storage spaces today, you can either have disks or what is known as enclosure fault awareness. In this model, you can set disk, enclosure, or the storage scale unit as the fault domain. We default to the storage scale unit, and that's where we want you to be for this type of deployment. And it's in a model that could be expanded in the future. The fault domain controls all data placement, all data repair, and all rebalancing activity. So that whatever data movement happens in the system or data repair, we always will observe the fault domain so that the data copies are placed so that we can tolerate 1 or more failures in the system. In the simplest case is I have a disk failure. It's probably also the most commonly occurring. If a disk fails in the system automatically repairs and regenerates data around that failed disk. Right? No user interaction needed. Then you have a failed disk sitting there. Then you as a user pull that disk out, replace it with a new disk. We bring it in, rebalance data. There's nothing for you to really do. If I click harder, it goes faster, right? If I have a temporary server outage, meaning like it could be that I need to replace a power supply, or that Tuesday at the beginning of the month comes around and I need to update my software, then when the server goes away because it gets restarted, no data is moved anywhere. The hypervisor that might be connected to that server transparently is moved to another node in the system, and we automatically do a data resync when the server comes back up, right? Because data might have been updated on the other copies of the extents while the server was away. So when the server comes back, we keep track of what was updated in between, and then we resync that data back on that server. Now, the most brutal scenario is the permanent server failure, because that potentially takes away a lot of data from your system. So the larger the server is, the more data you took away, right? So that repair, we leave control to a human being. And the reason for that is you could be in a position where you say, well, it was the motherboard that got fried. I can replace the motherboard in 4 hours. That's a lot faster than actually starting to regenerate 150 terabytes of data. Or the human would know, well, that server is never going to come back. I'm going to replace it with a brand new server and kick off repair. So depending on what the resolution is, the human controls and say, I want to have the system heal itself now. And here's an animation of a system that rebuilds itself from that.
Can you gracefully evict a node?
Yes, you can.
Want me to?
Yep. Here we go. So I'll hand it over to you, Michael. So you're speaking a little bit about REFS.
Hi, I'm Michael Gray. I'm the program manager for REFS. So in Windows Server 2012, we released REFS, a file system built from the ground up for scale, availability, and resiliency. That meant strong checksums on all metadata, optional checksums on user files to support workloads that didn't have their own resiliency guarantees built in. Having trouble with the clicker here. We did checksum verification on every single read to protect your hot data, as well as a background scrubber to protect your cold data. And whenever we detected problems, we'd go and heal that on the fly. So, for example, if we had a three-way mirror with spaces in REFS, we'll go ahead and verify the checksums on reads. Like, for example, imagine that's a bad checksum. We would go to the alternate copies or go read the parity data, go find a good copy, and use that to repair the bad copy. And again, all that happens on the fly for every read. Now, if you're down to the last copy of your data and that's still corrupt, we'll do everything we can to keep the volume online. We both do strategic duplication of metadata, along with those strong checksums that we keep. We can see, okay, this part of the file system is corrupt. Let's isolate that and keep that from spreading while keeping the rest of the volume online. Now, in theory, that's the same thing that CheckDisk does. But we don't have to do the scanning, we don't have to use the heuristics, and we don't have to take the volume offline. Now, with Storage Spaces Direct, we took this core of REFS and said, okay, let's go look at performance for Hyper-V and direct attached storage. So we implemented a bunch of optimizations for that scenario. The first thing we did is we added this feature that allows you to take portions of a file and copy them either within the file or to another file as a purely metadata operation without reading and writing the backing extents. Now what that does is that lets us take Hyper-V checkpoints as utilized by Hyper-V Backup and drastically reduce the amount of I/O they consume and drastically reduce the amount of time consumed when we merge them. So if if you imagine you've got a virtual hard disk backed by a parent VHDX file, and we took a stable point in time checkpoint for a backup application, and we kept that for a while so it could go copy it off somewhere. And all the new writes, as the VM was running, came into the child VHDX file, and we say, okay, we're done with that parent VHDX. The backup application has already gone and copied it off somewhere. We take all the new writes in that child VHDX, and in a traditional file system, we'd have to copy them back up into that parent VHDX file. But in ReFS, what we're able to do is simply remap those new writes from the child into the parent, and then go and delete the child. So we just take that and remap it straight up there. That little expansion, Hyper-V takes care of the details about which block maps to which. And then you're done. We have another new feature that lets you zero out portions of a file as a purely metadata operation. It's not a deferred zeroing. It's a pure metadata type thing. So you can say this portion of the file is 0, this portion of the file is 0, or this entire file is 0, and there's no zeroing I/O to the backing extents on disk. Now what this lets us do is create fixed VHDX files very, very quickly. If you imagine you have a VM with terabytes worth of storage, and you create fixed VHDX files, you have to do all this zeroing I/O, potentially write out terabytes of zeros. Well, with this, we simply mark it as zeroed in metadata, and that fixed VHDX file is created. Behind the scenes, not as dramatic, but it is going on there. Dynamic VHDX expansion, as they expand, there's also zeroing I/O that we're able to eliminate. So there's little peaks of I/O that you may see with dynamic VHDX files that we're able to eliminate. So now I'm going to do a demo of these new optimizations. So if this works out for me here, I've got two identical VMs. One's hosted on an NTFS volume on a Storage Spaces Direct setup. The other is hosted on ReFS on a Storage Spaces Direct setup. They both have some checkpoints here. I took an empty VM and I checkpointed it. Then I installed the Windows Technical Preview and I checkpointed it. And you know, I'm done keeping that checkpoint of the empty VM. I've got Windows installed. I don't need it anymore. So there's about 8 gigabytes of writes that I'm going to have to merge back. So on this ReFS VM, I'm going to go ahead here and say delete checkpoint. Yes, I really want to do that. And it's going to say merge in progress. You'll see it kicking off here, merge in progress. You don't see very much I/O, and it succeeded. That was it. About an 8 gigabyte merge.
Did you see it? I hope you didn't blink.
Now, for comparison's sake, here's NTFS. Exact same VM. I imported it onto a different volume running NTFS. Traditional file system here. And I'll go kick that off. And what you're going to see here is these perf counters I've got are showing a bunch of I/O as we're doing this data copy. So that's going to sit there and bake for a while. I think this is about 3 minutes. So it's a drastic difference in time, but really in I/O also. This drastically reduces the I/O cost of backups, drastically reduces the storage capacity cost, or capacity meaning bandwidth and IOPS of Hyper-V backup. That's just going to go for a while.
So that's all I/O happening in the system that is effectively wasted because that I/O could be given to actual user activity.
How would it be with Linux and ext4 volumes instead of NTFS?
I can't answer that authoritatively because I've never actually tried that there. I don't believe that they've got a remapping feature, unless that's been added recently. I haven't seen that. So the next thing I'm going to do is demo fixed VHDX creation with that file zeroing feature I mentioned. So I've got a PowerShell command line here that's going to go ahead and do that on ReFS. So I'm going to create a 15 gigabyte VHDX file. If I can highlight this line. So that's on a ReFS volume of 15 gigabytes, just because 15 gigabytes is convenient. And it's going to go ahead and create it. Done. I actually didn't practice these two demos back to back, so you're seeing the I/O from the previous checkpoint merge. So you're not able to see the lack of I/O. Oh, it's done. OK, so on this next one, you'll be able to see the I/O from NTFS. So I'm going to compare exact same thing, NTFS, 15 gigabyte fixed VHDX file, same storage space as direct setup, but different volume here. Do that in NTFS. And it's going to go through, it creates the file, and it does all the zeroing I/O. It takes a while. This 15 gigabytes isn't that big for a real storage spaces direct setup, but you can see it ticking along there, and you can see all the I/O it's generating, whereas you didn't see any of that on ReFS.
Yeah, it's pretty cool. Thanks, Michael. So while that is running, I'm going to do a little bit different demo. So the system that is backing, so what Michael showed was actually commands run on one of the 9 hypervisors we got connected here. I am going, in the meantime, I'm just going to go start some VMs. So I have a little script here that reaches across a bunch of hypervisors. So I'm just going to let that run in the background so we get some I/O workload going. So what you're looking at here on this screen, and sorry, it might be a little dense for the people in the back, but this is effectively device manager. So what you're looking at here is the storage devices in one of the nodes in the cluster we have. So if you look at it, we got a bunch of ATA, WDC, probably means it's Western Digital devices. There is about 20 of them. So those are my hard drives. They're SATA disks. And at the bottom here, I got 4 NVMe devices. So note the number 4. Now let's go take a look at the cluster. So this is a 5-node cluster. And so if I can bring together NVMe devices in a 5-node cluster, how many NVMe devices should I have? 20, right? So let's go take a look at the pool. So this is the pool that is defined in this storage cluster. And you don't have to count them. You can go look at the video later. There is exactly 20 NVMe devices. You can see the middle column here that says NVMe. So the purpose of this demo was to show 2 things. Not only can we utilize devices like NVMe in this type of system, we can also bring them together in a clustered high availability storage system. So let's see, we should have some workload now. So this particular performance window shows data bytes per second across the 5 nodes. And you can see that there is actually just I/O on 4 nodes. And that's because this cluster used to be a 4-node cluster, and I just added the 5th node. Right? So I didn't do any rebalancing yet, and that's exactly why all the I/O happens on 4 of the nodes. I artificially limited the I/O that each VM is doing, because each VM is running disk speed at full bore, but I use storage cores to throttle it down. So they only can push 100 IOPS per second each of the VMs, because I want to show you something. I want to issue the command that brings in the disks of the 5th node into play and starts the rebalancing process. And because that's a sequential operation, what you hopefully see is that a lot of throughput as we are rebalancing the system. So this is a single command. I'm just highlighting the other commands which was used to, add the cluster node and expand the pool. Those are the 2 commands that are above here. So I'm going to issue this command, and it's going to look at the system. It's going to look at all the extents that I talked about earlier, and then it's going to start remapping extents and moving them from one of the 4 nodes onto the 5th node to rebalance the data consumption across the cluster. And because this is a throughput counter, you can see that the system is now going full bore, moving data to other nodes. But our protocol is that user data always have priority. So if there's more user data, it takes precedence. And the rebalancing happens in the background. So that's pretty cool. It'll take a few minutes to complete because there is a lot of data in this storage system. So just going to leave that running as we return back to the presentation. That would be 5. So I believe that's your cue, Hector. So Hector will be speaking about storage management for private cloud.
Alrighty. Thank you, guys. All right, good afternoon, everyone. My name is Hector Linares. I'm a program manager in the System Center team. And so from a management perspective, we've been on a journey with the Windows Server team on SMB3 and enabling the ecosystem, both from a Microsoft software-defined storage perspective and also working with our partners like NetApp, EMC, Tintri, and others on enabling SMB3 as a protocol natively on their devices. So the model that we built is that we wanted to make sure management was actually consistent across all these devices. So we worked with the teams in Windows Server and Core Storage to make sure that we have a consistent management API called the Storage Management API that sits on top of all of these devices. We work with our partners, both internally and third party, to build providers that plug into this SM API layer so that System Center Operations Manager and System Center Virtual Machine Manager can sit on this consistent management layer. So this is what you see here. This session is going to be focused on a scale-out file server sitting on top of Spaces Direct, but what you have with 2012 R2 is scale-out file server on shared SAS, and also partners that have developed NAS devices that implement SMB3. We've also seen a very popular deployment model, which is scale-out file server on SAN, and I'll talk about that tomorrow on my session on Friday morning, which we've also automated to make sure that you can build up those scale-out file servers using other types of storage. So specifically, the investments we've made in Spaces Direct management is, first of all, we wanted to make sure that we brought all of the simplifications and ease of use and ease of deployment that we've done already in the existing product of 2012 R2, bring that forward into 2016. And so we start our journey all the way from discovery of the systems as part of bare metal provisioning and all the way up to provisioning the storage, creating the file shares, activating the shares to Hyper-V, and then enabling mixed mode upgrades and servicing of those devices, and also disaster recovery. So on the disaster recovery front, we're actually doing a lot of work with the storage replica team to enable sync replication automation between 2 sites, all orchestrated by Azure Site Recovery. How many of you have used Azure Site Recovery? Have been working with it in a proof of concept? Okay, and so moving past technical preview 2, we will actually automate the failover of scale-out file server shares with the workload from one site to another using a pure Microsoft software-defined storage stack. Today we use Hyper-V Replica. We also enable this with our storage partners on SAN, and now we're going to do this natively in the SDS stack that Microsoft has worked on. And so as part of the demo, I'm going to actually focus on bringing up a scale-out file server, scaling out, and some of the storage provision that we do. Bring this over here. All right. So what you're looking at here is the VMM console. How many of you have used VMM, had a chance to work with it or have it in production? Excellent. So this is 2016. So it's a consistent experience with what you have today on 2012. A lot of this work happens under the covers, enabling the infrastructure, but we want to make sure the experience is consistent with what you know today. So I'm going to switch over to the Fabric view, which is on the bottom left. In the Fabric, I've got servers, compute, and networking. Specifically in the storage side, I've got file servers that are under management. We manage all of the devices using a provider. So the Microsoft SDS software provider, storage provider, is actually built into the system. So when you build a scale-out file server, when we go manage that, the actual provider is built into the platform. So there's no additional software to install. But if we take a step back and actually start from no scale-out file server, what we can do, in the ribbon, I can go to Create, click on File Server Cluster, and actually I can start the bare metal provisioning process for scale-out file server. So for those of you that are familiar with bare metal provisioning of Hyper-V, we actually use a very consistent wizard experience. We leverage BMC through IPMI and Smash to start up a machine, do the PXE boot from WDS, and go through the entire process. So in this case, what I would have to input is a cluster name and the scale-out file server name. These are obviously two different IP addresses. In order for us to know what workflow to use, you would have to tell us up front if this is a Spaces Direct implementation or if it's shared spaces or SAN. So for the 2016, we've actually added this radio button where you can tell us this is a Spaces Direct implementation. Once you tell us this, internally our workflow knows not to enable MPIO and not to do some of the stuff we do today on provisioning. We actually make this very specific to a scale-out file server. And we also enable all of the features in the cluster and file server to ensure that this is a Spaces Direct deployment. So I've got two options here to actually specify the servers. The first one is to specify the computer name. Let's assume you've already deployed them, you've done WDS, and the OS is already up and running, IP address is available. You can specify the computer names just by giving us a credential and going off and adding a new one, and adding the existing ones. The other option, more interesting one, is actually bare metal provisioning. So we take a physical computer profile, which is our blueprint, that we go stamp out on each one of the server nodes, and this is what we use to actually deploy the OS and configure all the settings. So I give a credential for the BMC, which is a DRAC or ILO. This allows us to remotely manage the system, and we give a range of IP addresses. This is not the IP addresses for the cluster. This is the IP addresses for the BMC controllers. So once we have this into the system, you can specify computer name, you can specify any settings per machine, and then the end result of that workflow is a running file server. The provider's been added to VMM, we've done all of the storage discovery, and at this point I can actually go and configure the storage. So in this for this scale-out file server, I right-click, click manage pools. So I've already got an existing pool under management, and I can create a new pool if I want as part of this. But before I do that, what I'm actually going to do is go into the properties, cluster nodes, and I'm actually going to, I'm actually going to add a new node. So what the feature we've added here is scaling out a scale-out file server. So you can add file server nodes. You can do this both from bare metal and also from existing. So in this case, I've already got an existing machine. Oops. Damn it. All right. Give me 1 second here. It's 24. Okay. All right. And at this point, I would be able to add this scale-out file server. Sorry, the node. So once it's added to the cluster, and I probably got the wrong name, so I'll just hand wave over this. The node is added to the scale-out file server. We bring in all the physical disks, and now I can go and add those disks to the pool. So what I would do here, for example, go in, right-click on a cluster, scale-out file server, manage pools, click on the pool itself, hit edit, and now I can start adding physical disks to this pool that's already under management. So another option I can do is actually go create a new pool. So if I hit on new, pool 2, classify this so that I know if I'm providing a high IOPS storage or just something for archival storage. Hit next. I can specify all of the disks that I want to add into the system. I can also look at the physical location of all these disks, and I can know what nodes they're attached to. So once I hit next and finish, this will actually go and create the pool from those physical disks. Once the pool is created, all I got to do now is click on the file server, create file share, and this will actually go and create a file share from a pool. Now, under the covers, we take care of provisioning the virtual disk, ensuring that it's attached to all the nodes, initializing, partitioning, formatting the disk, making it a CSV, and adding the file share on top. And so we just give it a name for the share. We pick the pool that we want this from. If we want to overwrite the classification, you can do that. Otherwise, we inherit the name, or the classification. And then I would just give this a size. I would specify the file system that I want to enable, a 3-way mirror, and any other options from there. If I had SSDs in this pool, I would actually be able to enable tiering and specify the tiers per, the amount of space per tier. So now that the pool is finished creating, I'm actually going to show that. All right, so let's do that. I'll do pool 2. Next. Give it a size. REFS 3 mirror, and I will enable tiers. So once I do that, now I can specify if I want this to be heavy on SSDs or not. You got the capability to do that. We default to 10%. Otherwise, you can just leave it as is or configure it and finish. And this will do all the work under the covers to stand up that file share. At this point, once the file share is created, you accolade to the Hyper-V cluster, and you start deploying your VMs. Since we're using copy file 2 APIs from Windows, we can actually offload the copy of the file itself. So we're using SMB copy chunk, and you can go pretty much as fast as the system allows you to go. Right? So no need to wait for bits to actually deploy. We've actually offloaded that to the system itself. So at this point, I'm done. Hand it back to you. Thank you.
Good. All right. Uh-oh. There we go. So now we've got the system provisioned. Let's talk a little bit about storage monitoring. So the model we have today for storage monitoring really relies on the monitoring tool doing all the work, effectively. So the monitoring system collects all the information, and it's a barrage of information that it gets from the storage system, and then it has to perform state computation and health roll-up on top of that. That means the management pack needs to be tightly coupled with the topology, the version, the storage technology, etc. And the side effect of that is while we can probably figure that out, it really makes it complicated for anyone who wants to build expansions on that and create management packs on top of that. So what we're doing in this release is we completely reimagined how we're going to do storage monitoring. So we pushed the logic of understanding the system and the state of everything into the storage system. So it's the developers in my team, and my team is the Storage Spaces Direct team, that are putting together the storage monitoring health logic in a service that lives inside the storage system. And what that means is we really report up to the monitoring system on 3 objects. The storage subsystem is where everything around hardware-related will go up, like disk fails, etc., or node fails. Volumes, because those are important when you talk about hyperconverged. And file shares, those are important when you talk about the private cloud storage model. When a failure occurs, and you go and you remediate the failure, you no longer need to go in and manually say, oh, I remediated it. The system will know, and it will automatically remove the alert that was raised in the system. And because of this, the model that we implemented, the time it takes from the actual fault to occur, from when it occurs to it shows up in System Center Operation Managers, we're talking seconds, right? So no more large delay or anything like that. The alert specifies the urgency. So for example, if you have a 4-node cluster and one of them goes down, it's sort of important, but it's not immediately urgent because the system is still up and running. It specifies what the remediation action is. So it's like bring that server back up, for example, right? Whatever that means. And then, as I said, it automatically resolves when the issue is addressed. The other part is that the health logic, besides it being consumed by default by System Center Operations Manager, it also can be consumed through PowerShell, or you can consume it if you want to write your own that interfaces directly with the health service. So let's do a quick demo on this one. This will be a slightly different demo because that's my desktop. I'll log in here real quick. And I typed the wrong password. Okay, it was quick. That was better. Here we go. So let's take a look at this real quick. So this is System Center Operation Manager. If you look at the almost leftmost column, you can see the three objects that I was talking about. At the top, we got the storage subsystem. In the middle, we got file shares, and then we got volumes. Yes, we know we need to reorder them so they're more logical. Oh, it's arrows, right. So in this case, we're just going to do a very simple operation, which is, let's stop a cluster node, right? Effectively, that means that the node goes away from the system. So let's stop that. It goes down. We come back to System Center Operation Manager. We see that there is now an alert that there is a node missing. But notice that in this view, we're not also telling that there's 24 disks missing and 4 volumes or anything like that. It's the topmost important thing that happened in the system, because we know that all those disks went away because the node went away. So there's no point in telling you all this noise, because what you really need to fix is to get the node back online. So when we go take a look at the property on that particular error, you can see that the severity is warning because everything is still online. My pool is online, my volumes is online, my scalar file shares are online. The priority is high because you do want to make sure that you bring the server back up online quickly. And then if you look at the alert description, it says the reason is the server cannot be reached, and we would recommend that you start or replace the storage server to recover from this. So you do that. So basically the way we recover is by starting it again. Now it's started. And then you'll see come back here, and the alert will automatically remediate itself. The other thing you can do is you can actually go and explore the topology. So if we can take a look, we can see that we got the clustered Windows server at the top. It has a pool underneath, and on that pool is a volume. Now this is a very simple representation of one storage system with one pool with one volume. But you get the idea that you can do topology discovery through this. All right. So that was a quick one here. Let's go back to number 5. Switching gears once again, talking about hardware. So one of the key things that we learn in software-defined storage is that it does matter what you put together, right? You just don't go to some random store, pick some disks, pick some SSDs, pick some controllers, pick some random servers, and just throw it all in a box and hope that it works. So what we're doing with StorageSpaces Direct is that we have strong development partnerships. And you will see a slide in a moment who we're working with. We've got strong development partnerships with a number of our partners. And what we do with them is we work with them to define the platform. So we say, what is the platform that makes most sense to go? And then we pick the components and we decide on a configuration that matters to the scenarios that we're driving, which in this case is Hyper-V storage, right, or private cloud storage. Then once we've gone through that process, we put the system under an extensive validation. And there are really 3 levels of validation. One is we evaluate each component, so we put that under high stress. Then we put each node under high stress. And then finally, we put the entire solution under high stress. So we have... Sorry. So in case you were sleeping, you're no longer sleeping. I hope you were not. This should be exciting enough, right? So we build effectively what is called what we call the private cloud simulator. The private cloud simulator is a toolkit that we developed specifically around the development process of the cloud platform system that you might have seen in our booth, which is a full rack system that we extensively validated. And what we have done is we've taken that and we put it into the kit that we give every partner we work with so they can run the private cloud simulator on this system themselves. And we will run it as well with them. So that's important. The second part I want to say that for Windows Server 2016 Technical Preview, which is effectively today, right, or a few days ago, the prescriptive configurations that we're working on with our partners are still a work in progress, right? So they're still being defined, et cetera, et cetera. So if you can't wait, initial evaluation can be done using Hyper-V Generation 2 virtual machines. So a quick way to get familiar with StorageSpaces Direct is to bring up 4 VMs, attach some extra VHDX files to them and start installing Windows Server Technical Preview 2 and start putting it together. All the instructions are online at this link for how to get from a form cluster and up until having a Stored Spaces Direct running. And if you have feedback, you can either send it to me, but you can also use this link for user voice. We would like to hear from you if you got any feedback on the scenarios and what is working. And I will take positive feedback as well as negative feedback. There's multiple documentation resources. Of course, the most important one for this session is Stored Spaces Direct, but we also encourage you to take a look at cluster rolling upgrades, Storage Quartz, and Storage Replica, which are what I would call companion capabilities. Now, so let's look at our development partners. So we have a very strong relationship with a bunch of our partners, and we've already defined the platforms are in the process of working out the details. So you can see here there is a very rich partnership between us and these partners, and we very much appreciated their effort in working with us in bringing Stored Spaces Direct to market on at least one platform per company. There's an FAQ in the slides. I'm not going to read the entire FAQ because that's going to be me reading to you. You don't need that. But there is a bunch of stuff here. For example, I'll pick one here. Can I use Stored Spaces Direct with NanoServer? Yes, you can. That's one of the key things, is to bring down this very small image and bring it to storage as well. And yes, we will still support shared SAS, JBoss, etc. So there's a bunch of them. You can look at them on your own. Now, I do want to show you a little video. See if I can switch over to my machine here. Escape out of this. Storage rebalancing, still working. So what you see here, I'm going to pause it for a second because this is recorded with etc. But what you see here is a Stored Spaces Direct deployment, but the screenshots are from two hypervisors connected to that Stored Spaces Direct. The Stored Spaces Direct deployment is a 4-node system backed by SATA SSDs in each node, and each node has RDMA-enabled network adapters. Right? So you can see here we got some shares here. You can see the host that it's coming from is the same name across, or maybe it's a little bit difficult. Actually, give me 1 second. Help you a little bit here. Let me start that tool. Open this up. Oh, that's not what I intended to do. Pause it real quick. And then do this. So you can see the host name for these 4 shares that I'm connected to is the same. That's my scale-out file server. I got 4 shares. I got shares called the Micron SATA 1 and Micron SATA 2. And the same thing over on the other client that we see over here, SATA 3 and SATA 4. Now, what the cool thing about is, I don't know if you've noticed yet, but down here at the bottom, we showed perfmon in terms of data requests per second served by this Stored Spaces Direct system. So from this one hypervisor, I'm getting 600,000 4K IOPS out of that system, or to this client. And if you go over here, I get just short of 580,000 IOPS to this client. So that means if I add up these two clients, I get 1.1 million IOPS or more from a 4-node system. That's on average about 250,000 IOPS per node and more. Also, more importantly is, you can't really see that well in this one. I'm going to go back to this one. Oops. Look at the second line. Average second per data request, 1 millisecond. And that's as experienced by the application running on the hypervisor that is remote from storage. And that's all the power of being able to run SSDs and running RDMA. But actually, let's do one experiment. Have you ever wondered what the value of running RDMA really is? You heard our pitch over and over and over again. But let's take a look. Because further in the video, we actually do disable RDMA in the system. So you can see how the performance changes. So we're running, humming along. We're running 600,000, 580,000. We're still running nicely with 1.2 million IOPS, just short of that. And it'll come up. So let me just skip forward a little bit. So we're actually disabling RDMA right now on these two systems. I'm going to highlight the video again. Look at that number. So 306, from 600 to 360. So just by using RDMA, I get about 40% more IOPS out of the system. And it's the same thing over on the other node. 310,000. So I effectively, to me, it's like running without RDMA is like running a Volvo in a Formula 1 race, right? How can you compete if you don't have RDMA? Look at, I got 40% more IOPS. And if you go look at it, and you will find that yourself, look at this picture. What you don't know is that the CPU consumption on this system gave you this 40% RDMA without consuming more CPU. So you just got a lot more throughput without consuming additional CPU to process the data. So as you can see, there's plenty of space left to run all sorts of workloads in this system. I think that's pretty cool. And I hope you do too. Now, we will do more as we go forward, show more interesting demonstrations, but I want to make sure that you walk away with a couple of points on this. I'm going to switch back to this one. And so this was a technology demonstration of things to come from Microsoft Software-Defined Storage. So what you saw was two hypervisors over an SMB3 storage network fabric to a 4-node scale-out file server that is running Storage Spaces Direct. I just wanted to highlight for you that just because we run nodes with direct attached storage and we use an Ethernet network fabric, yes, it's enabled for RDMA, we can push a lot of data IOs per second in that infrastructure. You can imagine what could happen if we actually doubled the node count or tripled the node count, what we can actually push in this type of system. And here's a good screenshot of the two performance monitor counters you saw. So, very good IOPS. You saw the value of RDMA, right? My 40% was, by the way, just a loose calculation, not a scientific calculation. So in summary, before we start taking questions, and I hope there is a lot, Storage Spaces Direct, so what is it? It's for private cloud storage, either deployed as hyperconverged, where the hypervisor and the storage is collapsed on the same machine, or deployed as private cloud storage, or also known as disaggregated, where the hypervisors are running remotely from the storage system. We use servers with local storage. Again, highlight the value of driving down the cost because we can use SATA SSDs, or improving the performance because we can use NVMe devices. And it continues to be highly available and scalable. It actually is more scalable because we unlocked ourselves from the bindings of the shared SAS fabric. It enables these new scenarios, which included hyperconverged, that I mentioned, which we don't promote today. And again, I want to make sure there's no misunderstanding. This is not a replacement for storage spaces. This is an evolution of storage spaces as you know today. We just added the tagline direct to highlight the fact that it's direct attached storage. So with that, you can engage with engineering. So if you want to, potentially participate in our early adoption programs, surveys, and deep technical discussions, go to this link, sign up, etc. And then Hopefully you liked what you heard, or you liked the way we presented it. But please share your feedback with us on how you liked the session. And with this, I'm going to open up for questions. Is there microphones here? Other than that, yell loudly. Thank you. Got any questions?
Sorry, yes. Hi, so I have, I guess, 4 different questions. The first one is, I've noticed, obviously, a number of sessions, they push for REFS over NTFS. Has the rest of Microsoft kept up with that? For example, DPM? Are we going to be able to do out-of-gas VM backups on clustered storage?
So the question is, has the rest of Microsoft come up with the fact that we are moving towards REFS, specifically DPM? We're working very closely with the DPM team to bring DPM to be able to back up virtual machines that are running on top of REFS, and to have the DPM machines themselves live on top of storage that is serviced by REFS. We would have loved to have shown you a demo today. Unfortunately, that did not pan out, but this is a work in progress, and you'll see it in future technical previews.
Okay. So the second one is quick. You said you are... Sorry? The second one is quick. You said you are using SATA, so there's no iSCSI persistent reservation requirement? Sorry, there's no iSCSI persistent reservation requirement?
That is correct. There's no iSCSI persistent reservation requirements.
Is SMB3 loopback then supported in a scenario, for example, where you have 4 storage nodes and 2 hypervisors that are different machines that we're connecting with SMB3? Does that preclude the machines in this from partaking in that SMB3 connection?
So I think your question is, can we, with Hyper-V over SMB, run in a loopback scenario?
Right.
And the answer is still no.
Okay.
We won't support that yet.
And the fourth question, I'll just be quick with this. Do you have the capability to customize your enclosure IDs so that you can, for example, support a scenario where you'd have 2 blade enclosures or two failure domains that are expected to split half and half, so that you can know that at least one of your 3 copies is on half of your machines versus the other half?
So I'm not sure, I think you mean by the enclosure ID, you mean discussing enclosure services?
Yeah.
By definition, in that standard, every enclosure should have a unique ID. We understand that not all implementation is actually implemented that way. So we are, for the hardware partners that we're working with that has that challenge, we have a software workaround.
Okay, thank you.
Sure. Any other? I'm not sure who was first, but go ahead.
I'll go ahead. Can you elaborate a little bit on how writes are happening, either in a hyperconverged scenario or when the Hyper-V, let's say the Hyper-V host is remote? So is there some sort of SOFS affinity, or how is that working in practice? Because in the past we had issues where there was a lot of CSV I/O redirection happening, and we lose quite a bit of performance because of that.
So how does it work in practice when the hypervisor is remote from the storage system and you saw a lot of CSV traffic?
Yeah.
So we did a bunch of work in 2012 R2 where we actually, in storage spaces deployment, you know that there is a CSV owner node. Yep. One of them is the coordinator. And we redirect the traffic to that node so that the hypervisor goes to that node where the space is attached.
Okay. And how about in a hyperconverged scenario? How is that working?
So in the hyperconverged scenario, the VMs will run on one node, and the coordinator node might be on the second node. Yeah. And that's why we have the high-speed networking and low-latency networking between the systems to allow for that.
Okay. Another question is, was there some work done to basically raise a little bit the ceiling per node on the I/O performance? I was hitting a certain point where basically if I run basically I had 2 CSV, 1 assigned per node. If I basically add the 2, I was hitting, let's say, 8 gigabytes per second, but when I put it on the same node, I was only hitting 6 gigabytes per second. So is there some work that was done on that side?
So also in 2012 R2, we actually implemented a mechanism to balance the CSV coordinators across the entire cluster.
Okay, but it really per node, it looked like the ceiling was at 6 6 gig per second, more or less. So is there some work that was done to improve that?
I'm not sure exactly. Can we take this question
Sure.
a bit later? I would like to hear it, but I have difficulty hearing with the echo in the room.
Okay, sorry.
So
Hi, I was just curious what the recommended max pool size is?
the max what?
Pool size?
So with the Technical Preview 2, it's 240 disks.
Okay, so there's just disk limitations, not a max terabyte limitation?
That's correct.
Okay, so no limitation on size then, just disk limitation.
I mean, we have tested the 240 with 4 terabyte disk. So as 6 terabytes come out, I cannot, with the way these things work, I cannot see why the size of the individual disk would matter in this particular question.
Okay.
It's a matter of disk count.
Gotcha, thank you.
Certainly. Any other questions? I don't mind at all. Very good question. How do I determine which disk to read from? We do have a little bit of software in there that determines which one has the shortest queue length. And that's the one we read from. That's correct. No, so bear in mind that the file system construct is one layer above the actual virtual disk construct. So the virtual disk construct is like 100 gigabytes, so there's a 100 gigabyte extent. When the file system then maps its data onto this one, it might touch n number of extents, depending on how the file is laid out on the file system. So I don't know, it could be 3, it could be 15. That's correct. It was a 1 million read IOPS demo. We'll have more to come on that. So these were 40 gig Ethernet networks, yes.
Is tiering supported on Direct? SSD tiering?
Sorry, what?
Can you have an SSD tier for your storage on Direct?
So let me just say this. We are using the flash in the system for both buffering writes as well as a read cache. So you do have a tiering model in this system. But we are actually working on fine-tuning a bunch of these implementations, so I'm not going to go into too much detail on it at this point.
Okay.
So can we support all flash? That is something we intend to do. Yes. So how does storage cost fit in with all of this? So storage cost is implemented much higher in the stack. So that happens up at the file system layer and between the hypervisor and the file system. So we have various things around how we want to consume flash. That is one version of it is in what is in Technical Preview 2, but we're still exploring our options there. Any other question? If nothing else, thank you again for being here. And I will be available outside if you have further follow-up questions that you'd rather talk to me one-on-one. Thank you.